RF Man here. Today I want to talk about capacitors and inductors, specifically the resonant frequency, or what's commonly called the self-resonant frequency of these components. And here what I'm showing is this is the equivalent circuit for a capacitor. So of course we have the capacitor itself, but if we look at the equivalent model, we also see there's equivalent series resistance, what's typically called ESR. There's also leakage resistance, so we get a little bit of leakage current in this direction. And then we have inductance as well, okay, parasitic inductance in this case. And where does the inductance come from? It comes from the internal construction of the capacitor, the leads that are used with the capacitor, etc. So this is your typical model for a capacitor, and the important point here that I'd like to note is that you see the capacitor, you see the inductor. The inductor is in series with the capacitor. Okay, so just bear that in mind, because now we're going to take a look at an inductor. Okay, and here's the equivalent circuit for an inductor. So we have, again, equivalent series resistance, we have the inductor itself, and we have a capacitor. Capacitor typically comes from the windings being close to one another, and that creates some capacitance between each winding. Okay, so we have parasitic capacitance. Now you'll note the difference here, that the capacitor is in parallel with the inductor. So this is a parallel resonant circuit. So here we had a series resonant circuit, and here we have a parallel resonant circuit. So why is that important? Well, let's take a look. So here we're showing the frequency response of a capacitor, okay, and the capacitive reactance is equal to 1 over 2 times pi times frequency times capacitance. So this is the numerator, frequency is in the denominator. So as we increase frequency, we're going to see the capacitance decrease. Okay, and the capacitance will decrease until it reaches the self-resonant frequency, and then you'll see instead of capacitive reactance, okay, the impedance starts to increase again, but this time it's inductive reactance. So the resonant frequency is the point where capacitive reactance and inductive reactance are equal, so the two cancel each other out, and what's left here is just the ESR, or the equivalent series resistance. Okay, we see that up here in the model. Now let's look at the behavior of an inductor. Okay, inductance, the inductive reactance is equal to 2 times pi times frequency times inductance. So this shows us as we increase frequency, we're going to increase the inductive reactance. Okay, so it's exactly opposite a capacitor. Okay, and when we reach the self-resonant frequency, what we have left is the ESR. We saw that in the model here. And then what happens is the impedance starts to decrease again and becomes capacitive. So in this case, below the self-resonant frequency, the device is inductive, and above the resonant frequency, it's capacitive. So these are the two main differences that I wanted to point out. Now let's just go to the next page here and say, okay, so we have one is a series resonant circuit that we see here, and one is a parallel resonant circuit that we see here. We often call that a tank circuit as well. Okay, and we can calculate what the resonant frequencies are for these components. Okay, but the important point is when we look at the series resonant circuit, okay, it has a low impedance at the resonant frequency, and we compare that to a parallel resonant circuit that has a high impedance at the resonant frequency. So basically, the capacitor at resonance acts like a short, impedance is very low, and the parallel circuit here, the inductor, okay, acts as an open, so the impedance is very high. Okay, now you can go ahead and calculate these values. There are a lot of websites available, okay, where you can calculate the capacitive reactance, inductive reactance. Here's all the various formulas that are used. Okay, you can calculate the resonant frequency. Okay, and this shows, okay, what is the main difference between capacitive reactance and inductive reactance. So let's talk about that without getting too deep into the subject. What I learned in school was an interesting phrase called Eli the Iceman. So Eli is ELI. So the L in the middle is inductance. And what we basically have is that we have impedance that's created from the phase shift between the voltage and the current. And in an ideal capacitor, in an ideal inductor, we have a 90-degree phase shift. But unfortunately, we don't live in an ideal world, so we have these parasitic effects that affect the actual performance of these components. And we're going to actually look at that on the vector network analyzer in just a few minutes. So we have capacitive reactance measured in ohms. We have inductive reactance measured in ohms. Okay, the reactance or impedance is created by the phase shift. And as I said, in an inductor, okay, the voltage leads the current, ELI, and in a capacitor, okay, the voltage lags the current. So you have ICE. Okay, just remember the word ice, okay, and you see the voltage lags the current. We can also say that the current leads the voltage. So if I say the voltage lags the current or the current leads the voltage, I'm saying the same thing. And in textbooks, it's often referred to as the voltage. And we have basically leading here and lagging here. Okay, so give me a few minutes and I'll go ahead and set this up, and we'll actually measure the resonant frequency of both a capacitor and an inductor and take a look at how that is on the VNA and what it looks like on the Smith chart as well. Okay, so for this video, I'm using a nano VNA. I've made other videos showing how this particular instrument is used. I made a video on different types of filters, low-pass filters, high-pass filters, things like that. The purpose of this video today is not to discuss all the capabilities of the Nano VNA and discuss any of the features, but there is something I'd like to point out. Okay, if we look at the VNA, right, we have port 1 and port 2, and each port is 50 ohms. And what we're going to be doing today is a through measurement. So we're going to actually look at the throughput between port 1, which is S11, that's our return loss. We'll talk about that. And then we're going to look at port 2, which is our gain. We'll talk about that as well. Now, each of these ports are matched to 50 ohms. Okay, so we generate a sweep signal here. Okay, and then we go ahead and go back and read this signal. So if port 1 is 50 ohms and port 2 is 50 ohms, and we just have a throughput, I'm using a coupler in this case, okay, then if we go and we take a look at the Smith chart, which is here, okay, we see that the marker is pretty much in the center of the Smith chart, which is 50 ohms. So let's talk briefly about the Smith chart as well, and I'm not trying to make everybody an expert on Smith charts. In fact, I'm gonna try to avoid talking about dBs, decibels. It's not really necessary to grasp a full understanding here of what we're talking about. So here, this is the 50 ohm point. And what we have here is constant resistance circles, as you see there. Okay, and then these curves are impedance curves. So we have constant resistance, and then we have our impedance. So the top half of the Smith chart, okay, shows basically the inductance as a positive value, and the bottom half shows capacitance as a negative value. And when we talk about impedances, we're talking about complex numbers. So what does that mean? Well, a complex number has two parts. We have the real part, which is resistance. Okay, and that's what we're showing here, right? At 50 ohms, all our RF systems are normalized at 50 ohms. Okay, so that's this circle here. Okay, and then we have an imaginary part. We have plus J, which is inductive reactance, and we have minus J, which is capacitive reactance. So as we look at the resonant frequency of both the capacitor and inductor, we'll see how it changes with frequency. I'm running all these tests by sweeping the components between 10 megahertz and 500 megahertz. So we can actually take a look at the changes on the Smith chart, and we can see when does the component become inductive, when it becomes capacitive, etc. So give me a minute and we'll go ahead and set up the fixture and we'll do some measurement. All right, so now I'm back. What I have here is a fixture that I built that allows me to measure different components, capacitors, inductors, etc. And we're going to start by looking at a 12 picofarad silver mica capacitor, which we have in the fixture here. And we're going to be sweeping that from 10 megahertz to 500 megahertz. So that's the frequency that I'll be using for all my measurements. So what we see on the S11 chart, this point here is the resonant frequency of this component. So again, that's where the capacitive reactance and inductive reactance are equal. And if we go over and look at the marker, we see the frequency is about 400 and let's call it 23 megahertz. Okay, and the return loss is the same as the amount of reflected power. So what did we say? We said that a capacitor acts like a series resonant circuit. You have the capacitor, inductor in series, so it has a low impedance, acts like a short. So you basically have port 1 shorted to port 2. So this shows that the reflected power is very low. Okay, so we'd expect to see the gain very high, right? So this is the reflected power, this would be the forward power. So if our reflected power is low, our forward power will be high. So that's what these charts show, the return loss and the gain. And another way to say that is basically the reflected power and forward power. Now if we look at the Smith chart, since we have a very good match, almost 50 ohms, we see that our marker is right in the center of the Smith chart. Remember, we said that this is 50 ohms. Okay, and if we go to the SWR chart, okay, and this is what a lot of our ham radio operators look at, what would they expect to see? Well, if we had a good match, okay, at 50 ohms, we'd expect to see the SWRs at 1:1. And that's exactly what we're showing here at the resonant frequency. Okay, so now let's take a little closer look at this, okay, and we'll get a better understanding. We said that some of the parasitic inductance is caused by the leads of the component. So what I have here is a component. I trimmed the leads, pretty much what you'd expect to see if it was mounted in a circuit board. Okay, but let's go ahead and just take the same component, 12 picofarads, same manufacturer, and we'll go ahead and put this in the fixture. Okay, like that. Okay, and we're going to go back and re-sweep this now. So we'll go back to the video monitor here, and we'll sweep it and see what the effects are. Remember, we're adding more inductance, so we'd expect the frequency to drop. Okay, so we see a shift in the resonant frequency. Let's move the marker down here. Okay, and let's take a look here to see marker 1, 230 megahertz. So it dropped almost 200 megahertz just from adding the component with the longer leads. So this is why it's important when we're working with RF to keep our lead lengths short, because we can change the frequency response of our components. Now, there may be some cases, and Motorola did this a lot in their bipolar amplifiers, their push-pull amplifiers. In the feedback circuit, they used an RL circuit. And the L in the circuit was just the lead lengths of the resistors. And they actually showed the inductance of these lead lengths on the schematic, about 20 nanohenries or so. And they were using the inductance of those leads as inductors. So there are times when you might want to use the inductance of the component and use a longer lead length, but in most cases we do not. So what did we say here? We're at the resonant frequency. That's when the capacitive reactance and inductive reactance are equal. But watch the Smith chart. Okay, if I go below the resonant frequency, what do we see? The marker moves to the bottom half of the Smith chart, which is capacitance. All right, and then we go ahead and go above the resonant frequency, and what do we see? The marker moves to the upper side of the Smith chart, which is inductance, right? And that's exactly what we said, okay, that below resonance we have capacitance, and then we have the resonant frequency, and above resonance it becomes inductive. So that's what we're showing here on the Smith chart. So next, let's take a look at an inductor and see how that behaves. All right, so now I'm back. This time we'll be measuring the resonant frequency of an inductor. Now, one thing to note here is that a lot of inductor manufacturers will include the self-resonant frequency of their components in their data sheet. So you see the second line from the bottom, SRF, self-resonant frequency. It's 120 megahertz. Okay, so we're going to measure this and see what we get, but let me point out I did a little bit of investigation to see what standard they use, and they are using components with shorter lead lengths in their test methodology. So we'll probably get a little bit different results as you've seen previously, because I got the full lead length of this inductor. Okay, so we're going to go ahead and sweep this. And again, I'm sweeping from 10 megahertz to 500 megahertz. I haven't changed that. Okay, but now what do we see? Well, we see something very different. In fact, it's exactly opposite the capacitor, right? What did we say? That an inductor with parasitic capacitance acts as a parallel resonant circuit which has a high impedance, right? We can consider that an open. Okay, so here's our return loss. Okay, and we can see at the resonant frequency there, the return loss is quite high. Okay, it's acting as an open, so we have a lot of reflected power. Okay, going back into our transceiver. If this was basically a ham radio and say a transmission line and antenna, we'd have a lot of reflected power because of the mismatch. Okay, so what happens to the gain? Well, of course, when we have a lot of reflected power due to impedance mismatch, the gain drops all the way down here. Okay, now let's take a look at marker 1, and let's see where we're at here. Looks like, move over a little, there we are. Okay, about 102 megahertz. The manufacturer said 120 megahertz, but the difference can be explained by the longer lead lengths that are used in my test versus the manufacturer's test. But it's reasonable, and we see again, return loss very high, a lot of reflected power because of the high impedance. The gain is very low, okay? And we look at the Smith chart here, we see it's on the bottom half, so it's inductive there. And if we look at the SWRs, we have basically, this is S11, SWRs are V SWRs, okay? We have a 13 to 1 mismatch at the resonance. So it's quite high, Okay, and what did we demonstrate before? If we go below the resonant frequency, it's going to be inductive. If we go above the resonant frequency, you see here, sorry about that, you see here that it's capacitive, right? We're on the bottom half of the Smith chart, so it's minus J or capacitive, okay? And if we move it up, then you see it becomes inductive here, okay? So I thought this would be an interesting topic to discuss. It's important to understand resonant frequency or self-resonant frequency when we're using components like capacitors and inductors at higher frequencies. And we expect the capacitor to behave as a capacitor, but that may not always be true, depending on the self-resonant frequency and the application of the component. And the same with an inductor. We know that, sure, the inductance is going to change with frequency, but we expect it to behave as an inductor. But as we can see here, okay, above the resonant frequency, it becomes a capacitor. So I hope this was interesting for you. And yeah, leave your comments. RF Man. Thank you.